Hello everyone. In this lesson we're going to talk about some applications of the potentiometer wire that were not discussed earlier. Let me begin by stating that this is the fourth lesson on this topic. In the first lesson we looked at the principle of the potentiometer wire and its calibration. The second lesson we looked at some of the applications of the potentiometer wire, and this included determination of the EMF of a cell, determination of internal resistance of a cell, measurement of resistance of a resistor. Then in the third lesson we looked at some of the calculations based on the first three applications that we discussed. Now in this lesson we're going to look at more applications of the potentiometer wire. That potentiometer wire can be used for the calibration of an ammeter. The circuit diagram that you see on your left hand side is the diagram that is used for that purpose. It consists of a standard cell, a standard resistor, a rheostat, an ammeter, and of course a driver cell, which maintains a steady current in a uniform resistance wire AB. Now, when the circuit is connected as shown, the switch K is first thrown to position 1, and the jockey is moved along the wire AB until a balance point is reached. And that balance point is reached when the galvanometer shows no deflection. In other words, no current flows through the galvanometer. So the balance length from point A up to that point when the galvanometer shows no deflection is measured, and that corresponds to the distance represented as LS. So the EMF of the cell is going to be equal to K, the PD per centimeter of the wire, times the balance length. That is the equation 1 that you see over there on your right hand side. Then the switch is thrown to position 2. The rheostat is adjusted until the ammeter reads the minimum value it is possible to read, and then the jockey is moved along the wire until the balance point is reached. So this time it is going to be the PD across the standard resistor RS, which is proportional to the PD from point A up to the point where the galvanometer shows no deflection, where the jockey is. So we then measure the balance length, this time referred to as L, and then we equate the PD across the resistor RS, which is IA times RS, will equal to K times L, where K is the PD per centimeter and L is the balance length. So the experiment is repeated for other settings of the rheostat. In other words, when the current is adjusted, current flowing through the switch, current flowing through the resistor RS having been varied. So, but for all those cases, the equation remains IA RS is equal to KL. So using the two equations, we can make IA the subject. So we get the ammeter reading, the ammeter calculated value, and also take note of the ammeter reading for each of those cases. And then you plot a graph of current IA against the current as represented, as determined from the ammeter, and then that constitutes what we call the calibration curve. Plot a graph of IA against I, which is the value read from the ammeter. That gives you the calibration curve. So that is how an ammeter is calibrated using a potentiometer wire. Another application of the potentiometer wire is the calibration of a voltmeter. the diagram is almost the same as the one for the previous case that I've just discussed. We again have a standard cell, a switch which can be thrown into two positions, 1 and 2, and the rest is the same. So when the switch is thrown to position 1, again the jockey is moved along the wire until the balance point is reached. So ES is equal to KLS. We have said that over and over. Then switch is thrown to position 2. The rheostat is adjusted until the voltmeter reaches the minimum value. Then the balance length is determined when the galvanometer shows no deflection. So the PD VA is equal to KL. So making VA the subject using those two equations, the first and second equation, we notice that VA is equal to LES over LS. So that gives us the reading. Then we also take note of the voltmeter reading, and then I repeat the experiment for different settings of the rheostat. So a graph of VA against V, if we use maybe VR to represent the reading from the voltmeter, a graph of VA against VR will constitute the calibration curve of the voltmeter. So that is how a potentiometer wire is used to calibrate a voltmeter. The potentiometer wire can also be used to measure current through a resistor. This is current which is produced from another circuit that is not shown in the diagram, that is not shown here. So if current passes through that wire and then you find the PD across that wire because PD is equal to IR, so that, and then you move the jockey along the wire until the balance point is reached, then you measure the balance length. The value IR is going to be equal to KL. But now to get the value of K, we need to use a standard cell. That is what you see on the right hand side, that with a standard cell you can balance the cell on the wire until the balance point is reached and get the balance length LS. So from here you get the calibration constant and substitute it in the other equation. Here are those two equations. Here the first one with a standard cell, the second one without a standard cell, and then make I the subject and you obtain the value of the current. So that is how you measure current using a potentiometer wire. Not quite different from the case which was involving calibration of the ammeter. Lastly, let's look at how to determine the EMF of a thermocouple. In determining a thermocouple, first of all, constitutes of two metals which are joined together at two different junctions, which are kept at different temperatures. So that sets up a thermoelectric EMF, a very low voltage, very low EMF. So that is what a thermocouple is. It has got very low voltages that are set up whenever two metals are joined to form two junctions at different temperatures. Now, in order to determine that very low EMF, we need very high resistance in the circuit of a potentiometer wire. This diagram is not fully labeled. We can say the extreme end of the wire is A and the other end is B. And then we move the jockey. This is the thermocouple, the lower section of the thermocouple. The jockey is moved along the wire until a balance point is reached, and the balance length is determined. Now, then we can repeat the experiment with a standard cell. The high resistance in the circuit helps reduce the current so that the EMF along the wire is very low. The potential difference along the wire is going to be low to the order of that of the thermocouple. So when you have a standard cell connected to it, there will be a point when a balance point is determined. So you get the calibration constant K, which is going to be equal to ES over LS. Now, if V represents the EMF of the thermocouple, V is going to be equal to KL, and the value of K can be substituted, is obtained from the second part when you use a standard cell, so the EMF of the thermocouple is determined. Thank you very much for listening to me. That is how we use the potentiometer wire in determining the various in determining the EMF of a thermocouple, calibrating the voltmeter, and also calibration of an ammeter, as well as determining current flowing through a resistor. Thank you.